Hello, I'm Mikhail Raskin and I will tell you about our joint work with Mikhail Blondin on complexity of reachability in affine vector addition systems with states. In this talk I will start with some context, like the definition of vector addition systems and their integer relaxations and their affine extensions. Then I will give you an overview of the state of the art about the complexity of reachability in some of the integer relaxations of affine extensions of vector addition systems. Then I will give definition of classes of Z-A-VASS, which are the setting for our complexity results. Then I will present the main result of our paper, namely the characterization of complexity of reachability for all classes of integer relaxations of affine VASS, as well as a formalization of a Folklore conjecture about a non-relaxed affine VASS, which we have also proven. I will give a short overview of the components needed for the proof, and finally there will be some conclusion and discussion of the remaining questions. So what is a plane vector addition system? Well, we need to choose the dimension d, and then our states will be non-negative tuples of length d, and the allowed transitions between states are described by a finite set of integer vectors. It is often convenient to model a system as a vector addition system with states. In this case, we have a finite set of states, and now the transitions are transition between states, which are also equipped with the transition vector. This model actually has the same expressive power as plane vector addition systems, but it is a more convenient starting point for relaxations and extensions. Vector addition systems, or vector addition systems with states, or Petri nets, are a central setting for verification. They are used both to model systems with complicated internal states and large distributed systems with a lot of relatively simple agents. However, they do have some drawbacks. On the one hand, they are known to be hard to verify, and it has been relatively recently proven that reachability is actually tower hard. On the other hand, they are still not expressive enough. For example, the barrier synchronization primitive, when we require that all the agents may take some step at the same time, is impossible to express with vector addition systems. If we want to make verification simpler, we can consider related models with much simpler reachability. One popular option for a model with a simpler reachability is an overapproximation. We allow negative coordinates, so our states now live in integers to the power d, times q, the finite state. This overapproximation immediately brings the complexity of reachability down to nearly NP-complete. Note that in this case, states do matter. Integer vector addition systems with states are not modeled directly by integer vector addition systems without states. On the other hand, if we want better expressive power, then we probably will make our model more complicated instead of simpler. For example, we could allow transitions between states to be equipped with arbitrary affine transforms instead of just vector additions. This improves the expressive power, but of course leads to undecidable reachability problem. To summarize, integer relaxations of the notion of vector addition systems with states give us low complexity of verification, but of course low expressive power. On the other hand, affine vector addition systems with states provide us with high expressive power at the cost of undecidable reachability relation. One could ask, can we just do both? Yes, we can, but this is still undecidable in the general case. But maybe we do not need all the affine transforms. We can consider transforms x maps to ax plus b for arbitrary vector b, but for matrix A with some property, and ask whether some properties guarantee better reachability complexity. So what properties of A can we demand, and what will we get as complexity of the reachability problem? For a trivial example, we could start with not allowing anything, in other words, requiring that A is exactly the identity matrix, and in this case, as we have already mentioned, we obtain an NP-complete reachability problem. If we want to have a real affine transformations, then we can allow, for example, resets. In other words, we allow A to be a diagonal matrix with all the matrix elements being zeros and ones. In this case, the reachability problem is decidable and NP-complete. A more interesting extension is allowing copies. In this case, we allow some counter to forget its old value and to take the current value of another counter. Unfortunately, with more interesting expressive power also comes more interesting reachability problem. In this case, deciding reachability is a p-space complete problem. The same holds if we do not allow copies, but instead allow transfers. A transfer is taking two counters, putting the sum of the two counters in one of them and 0 into the other one. Yet another extension with p-space complete reachability problem for integer relaxation is a coordinate permutation. In this case, we allow A to be an arbitrary permutation matrix. In all of these results, we consider arbitrary dimension and a specific class of Z-A-VASS. There are also some results that hold for an arbitrary fixed dimension and a fixed set of matrices. For example, we might know that the monoid consisting of all the products of the matrices corresponding to transitions is finite. Then the problem of reachability in the integer relaxation of any vector addition systems with such matrices is decidable in exponential space. We could also consider a case of just a single matrix which has infinitely many distinct powers. However, it turns out that for such a restriction on affine transformations, there are examples of Z-A-VASS both with decidable and with undecidable reachability problem. We have seen what happens when we add resets or copies to the Z-VASS. For the modeling applications, it would be nice to be able to say, okay, we add these operations, and that's the complexity of reachability problem that we get as the result. In other words, we would like to characterize the complexity of reachability problems for all classes of Z-A-VASS. Of course, to solve this problem, we should start with defining what is a class in the first place. We want the notion of a class to correspond to adding some operation to the Z-VASS. When we define resets or copies, we define some operation that can be later applied to any counters we select. Moreover, for copy, we can also choose in which order we apply the copy to the two counters. This guides our definition of a matrix class. We say that a matrix class for extending vector addition system with states or extending integer relaxation of vector addition system with states must be closed under two operations. It must be closed under addition of unaffected coordinates, as we can always choose to apply our operation only to the first few counters, and it also must be closed under conjugation by coordinate permutations, which corresponds to choosing in which order to apply some operation to the chosen counters. In matrix notation, we can say that if we have a matrix A, then adding coordinates yields a block matrix with blocks A and identity of some size on the diagonal and zeros off the diagonal. And the conjugation is written just as multiplying by a permutation matrix and by its inverse from the two sides. This corresponds to reordering the counters so that selected counters go in the correct order when we apply the operation defined by A, but then bringing the counters back into their places. Note that we do need to bring the counters back to their original positions. Indeed, allowing just the identity matrix yields an P-complete reachability problem for the integer relaxation, while adding the permutations makes the reachability problem P-space complete. So we need our definition not to give all the permutations for free. It is easy to see that the previously discussed classes of vector addition systems extended with resets or copies or transfers or permutations are all closed under these operations. Now that we have defined the classes of affine extensions of VASS, we can characterize the complexity of reachability problem for all classes of Z-A-VASS. Notice that for all the classes of Z-A-VASS that we have discussed before, the reachability problem is one of P-complete, P-space complete, or undecidable. This is no coincidence. In fact, the central theorem of our paper shows that for any class of Z-A-VASS, the complexity of the reachability problem always has to be one of these three. Moreover, it is even easy to find out which of the three. To describe our trichotomy, we of course need to define some matrix classes. We remind that the reset matrices are diagonal matrices which only have 0 and 1 entries. Pseudo-transfer matrices are matrices with elements 0 and plus minus 1, such that each column has at most one non-zero element. Finally, pseudo-copy matrix is a matrix again with elements only 0 and plus minus 1, such that each row has at most one non-zero element. This is enough to state the trichotomy conditions. Specifically, consider the matrix class C, for which we want to learn the complexity of the Z-A-VASS reachability problem. If C turns out to only contain reset matrices, and of course identity matrix is always a reset matrix, then the reachability problem is NP-complete. If C contains some non-reset matrices, but all the matrices in C are either pseudo-transfer or pseudo-copy, then the reachability problem is P-space complete. Finally, if the previous conditions do not hold, then reachability problem is undecidable for this class of Z-A-VASS. Of course, there might be specific Z-A-VASS in the class for which reachability problem is decidable anyway. We now turn to the affine extensions of VASS as opposed to the affine extensions of integer relaxations of VASS. It is known that VASS with resets have undecidable reachability, and there was a conjecture in the Folklore that any meaningful affine extension of VASS has undecidable reachability. Of course, the notion of meaningful extension requires some formal definition, and fortunately the notion of matrix classes and the extension classes that we have introduced allows us to give such a definition. Our main theorem about affine extensions of vector addition systems with states in the non-relaxed case says the following. Consider a matrix class C, and we want to learn the reachability problem complexity for the corresponding extensions. If C only contains permutation matrices, then A5.B reachability for the matrix class C is equivalent to the standard VASS reachability. And otherwise, in all the other cases where the extension is actually meaningful and changes something, the reachability problem is indeed undecidable. Now let's look at the proof components, again starting with the case of Z-A-VASS, the affine extensions of integer relaxations of vector addition systems with states. Of course, we use the facts that were previously known, such as NP completeness for the case of reset, P-space completeness for copy, transfer, permutation. A brief idea that for P-space completeness we try to model a Turing machine, and basically our modeling guesses the memory contents every time when the tape is read, and we kind of double count the guesses, and the final counts of the guesses will match if and only if all the guesses have been correct during the execution. Then we also need that if the matrix monoid is small enough, then the reachability problem is in P-space. We also need undecidability if we allow doubling of counters via a reduction from post-correspondence problem. It turns out that all the classes where reachability problem is decidable in polynomial space actually are pretty small closed classes, and so the small matrix monoid case covers all of them. And it's easy to see that the reset case is exactly the same as was known before, so the positive results are all there. Thus, once the boundaries in the trichotomy are known, we need just to prove the hardness of reachability problems for all the matrix classes. Therefore, we just need to construct the reductions. To prove the P-space hardness for pseudo-copy, pseudo-transfer case, which includes, for example, permutation matrices and also includes the diagonal matrices with -1 in some of the diagonal cells, we need to adapt the P-space hardness construction which models the Turing machine by guessing the cell content on each step and double counting the guesses. We need to consider the combinatorics of how exactly the non-zero matrix elements are located inside the matrix, and it turns out that there is just a small number of sufficiently different cases, and for each case we can propose a specific memory encoding which allows the guess and double count construction to work. To show undecidability for each class not covered by NP completeness or P-space completeness conditions, we start by showing that we can obtain a matrix entry which is not 0, +1 or -1. Afterwards, we use this larger than 1 entry to produce a matrix with arbitrarily large entry dominating all the other entries. To do that, we consider that we can take one value and more or less double it if we use fresh auxiliary counters with 0. And then we can boost this value, transferring it from counter to counter, using fresh auxiliary counters with 0 on each step. Of course, we do not have unbounded amount of counters. but it turns out that we can reduce the oldest auxiliary counters because they are almost zero in comparison to the current value we are boosting. In a sense, you can imagine a cyclotron where a particle goes round and round, gaining more and more energy. It turns out that the resulting operation behaves in a way similar enough to doubling to be able to perform post-correspondence problem reduction. Now let's turn to the proof strategy for affine vector addition system with states without integer relaxation. We will use the known fact that VASS with resets already have undecidable reachability. First of all, we consider the case of permutation matrices. In this case, we use the fact that for each dimension there is just a finite amount of permutations, so we can put them into the state. Next, we consider the case where an operation is described by a matrix with a negative entry, but a matrix with a negative entry can be used to simulate a zero test. Indeed, applying a matrix with a negative entry to a lot of zero counters and one counter which is either zero or positive yields either all zeros or a negative value which is not allowed. Now, if we have a non-negative matrix class which is undecidable for the integer relaxations, it turns out that by exactly same construction, by the exactly same reduction, we can also prove its undecidability for affine VASS without relaxation. Finally, there is the remaining case of having a matrix class of either only pseudo-copies or only pseudo-transfers. And on the other hand, we know that they are not just reset matrices. And in this case, we need to again look at the combinatorics of non-zero elements in the matrix and find a way to simulate resets. It turns out that in each case there is some way to simulate resets, which concludes the proof. So, to conclude, what we have achieved is classification of A-VASS and Z-A-VASS reachability complexity for all classes of matrices. Of course, it is also interesting what is the complexity of the reachability problem in individual instances of Z-A-VASS, when we have a specific state set and specific list of transitions. This is currently a work in progress, but we hope that we have found a way to prove that the reachability problem can have arbitrary complexity at least between some polynomial complexity and undecidability. Another related problem, which can be said to be intermediate between the two problems above, is the complexity of reachability problem for a given matrix monoid. Unlike the classes of matrices, we do not have the closure properties here except the closure under multiplication, and the dimension is fixed. And unlike individual instances of Z-A-VASS, while the matrices are fixed, the individual states and the transitions between the individual states can have very different structure. In this case, we do not have any specific conjectures, and so this remains an open problem which we find also of interest. Thank you all for your attention.